Welcome back. So white wine often contains the preservative sulfur dioxide, SO2, which actually helps protect its colour, stops it going brown. But sulfites can be measured using a redox titration. And one of the things we're going to look at in this lesson is how we conduct redox titrations. So the topic for this lesson is volumetric analysis of redox reactions. Last year in year 11, you did titrations with acids and bases. Acids and bases aren't in the year 12 course, but volumetric analysis with redox reactions is. And that's what we're going to discuss today. So the key knowledge dot points, volumetric analysis, including calculations of excess and limiting reactants using redox titrations, but excluding back titrations. So direct titrations are what we're after. And also measuring the degree of unsaturation of compounds using iodine. You'll recall from year 11 chemistry that the equipment that we use a pipette that has an aliquot that's dispensed from it. And we have a burette, and the volume that comes out of the burette is the titer. We also have conical flasks that the redox reaction is taking place in. And we also have sometimes volumetric flasks, which are often used for dilutions, where an aliquot from a pipette is taken for dilutions. Okay, so the steps in a titration, an aliquot, often 25.00 mil or 20.00 mil, is taken of a solution which is added to a conical flask. There was actually a multiple choice question on the 2023 VCEE exam that talked about the technique of using the pipette within the conical flask. The assessors decided to award the mark to everyone because it talked about tapping the pipette against the sides of the conical flask, whereas the actual technique says to touch the tip of the pipette against the conical flask. Now, there will always be a bit of remaining solution in the tip of the pipette. That's normal. You shouldn't try and blow it out or anything, because that's part of the calibration of the pipette. Once we've got our aliquot in our conical flask, we may need to use an indicator. In redox reactions, sometimes the oxidizing agent or reducing agent is self-indicating. Other times an indicator such as starch might need to be used. And the reaction takes place in the conical flask, which is swirled to mix the contents. An initial reading is taken to 2 decimal places, and then the tap is opened and a final reading is taken to 2 decimal places, where the first permanent colour change is observed, and that is the end point. So we've talked about the pipette, the aliquot, the burette, and the titer. The other keywords in this are the titration itself, which is the volumetric analysis. The equivalence point is when the molar ratio of the reactants is completely balanced, whereas the end point is the point that's observed when the colour change occurs. It's really important to read the meniscus at eye level. This is to avoid parallax error, where if we don't read at eye level, we read above or below, we misread the bottom of the meniscus. So you must read the bottom of the meniscus at eye level. So that means that you don't need to fill the burette right to the very top up to 0.00 mil, especially if you're not tall, and I'm certainly not tall. So I always fill up the burette so that when I'm standing, that I can read the meniscus at eye level. And so that's really important. The standardized solution can be in the aliquot, so in the conical flask, or in the titer, so in the burette. So one of the solutions is a standardized solution. In a titration, we want concordant titers. That means 3 or more titers that fall within the maximum range of 0.10 mil of each other. An indicator is sometimes used, and it's a substance that changes colour to indicate the endpoint. A standardised solution is a solution that has an accurately known concentration. And the meniscus is this curved sort of effect, and we read the bottom of the meniscus. Okay, it's important to be aware of some possible errors that occur with titrations, and this is a typical exam type question. So the situation is listed here in this table. So it's got to do with what solution we rinse this glassware with. So the right procedure is to rinse the burette with the solution that's going into it. An error could be if the burette was rinsed with water. And the effect that would have is that the solution in the burette becomes diluted because of the water drops that have remained. If the unknown solution is in the conical flask, this will lead to an overestimate of the concentration. Or if the unknown solution is in the burette, it will lead to an underestimation of the concentration. The pipette should be rinsed with the solution that goes into it. If an error would be to rinse the pipette only with water, again, that means that the solution in the conical flask becomes diluted because there's water drops there. If the unknown solution is in the conical flask, it will lead to an underestimation of the concentration. If the unknown is in the burette, it will lead to an overestimation of the concentration. Conical flask should only ever be rinsed with water. Same with a volumetric flask. If, though, the conical flask was rinsed with the solution that's going to be put into it from the aliquot or from the pipette, that would lead to an overestimation if the unknown is in the conical flask, or an underestimation if the unknown is in the burette. And that's because the solution in the conical flask will be a higher concentration of solute than should be from the aliquot. If the correct technique is to stop the titration at the first permanent colour change at the endpoint, but if the endpoint is missed, then if the unknown is in the conical flask, you'll lead to an overestimation of the concentration. Or if the unknown is in the burette, it will lead to an underestimation. So it's important to repeat the titration several times to get concordant readings where you don't miss the endpoint, that you don't overshoot, because that means that you're going to have a bigger discrepancy between the endpoint, which is the colour change, and the equivalence point. So in a titration, often the first titer is overshot, or the indicator, the endpoint of the indicator is missed. Too much of the titer from the burette is added. So that's repeated until concordant titers are received. We need 3 concordant titers with a maximum range of 0.10 mil, which is about 2 drops, which is the standard resolution of a burette, plus or minus 0.05 mil. Okay, so we've talked a little bit about the process of titrations. Now we want to talk specifically about redox titrations. One of the important skills is to write balanced half equations so that you can write a balanced overall redox equation. You remember that we can use COEs in acidic conditions and CONERs in basic conditions. COEs stands for K for the key element, which is not oxygen or hydrogen. The next step is balance oxygens by adding water molecules to the opposite side of the equation. Then you've introduced hydrogen, so you balance hydrogen atoms by adding protons, H+. Next is to balance the charge by adding electrons to the more positive side, and finally adding states. There's an extra step in alkaline conditions or basic conditions. Alkaline and basic mean the same thing. It's K for key element that's not oxygen or hydrogen. Do the same step that we did with COEs. Balance oxygen by adding water molecules. Then balance hydrogen by adding protons. But then there's a neutralization step because OH- will react with H+ to form water. So in alkaline or basic conditions, what we need to do for every proton we have, we add a hydroxide ion to both sides of the equation, and then we neutralize our protons with hydroxide ions to produce water, and then we simplify the waters on both sides of the equation. Then we balance charge by adding electrons, and then finally we add states. Once you've got two half equations, then you can write a balanced redox, overall redox reaction by cancelling electrons, cancelling the electrolyte, which is either H+ or OH-, for example, and simplifying water molecules. So let's look at a worked example. Write a balanced half equation for the oxidation of magnesium metal to magnesium oxide in acidic conditions and alkaline conditions. First of all, using COEs. So we have magnesium metal, and we're told we're producing magnesium oxide. So the first step is we check that we're balanced for the key element. The key element in this half equation is magnesium, and we've got one magnesium on each side of the equation. So that's balanced. Next thing we have to do is balance oxygen by adding water. We've got oxygen in magnesium oxide, so we add a molecule of water to the left side to balance oxygen. So that's balanced. Now, from the water, we've added 2 hydrogen atoms. We balance that by adding 2 protons to the opposite side. So now we're balanced for that. We need to make sure that the charge on both sides is equal. The charge on the left side is 0 because magnesium and water have no charge. But the 2 protons add a 2+ charge to the right-hand side. So we add electrons to the more positive side, which is the right-hand side in this case. We add 2 electrons to balance the charge of the 2 protons. So now overall on this side, the charge is 0. And then S for states, where we're told that we had magnesium metal. So the state of that at room temperature is a solid. Water is a liquid. The magnesium oxide is a solid, and that could sometimes be given in the stem of the question. H+ ions are aqueous because they're dissolved in water, and electrons don't have states. Using CONES, we go through the same steps of adding water molecules and protons, but in alkaline or basic conditions, we need to have hydroxide ions. So what we do, we had 2 H+ ions in our equation as we're building it. That means we need to add 2 hydroxide ions to both sides of the equation. We need to do the same to both sides. So now we've got 2 hydroxide ions on the left, but we've got 2 hydroxide ions and 2 protons on the right. They together make 2 molecules of water. Now we've got water on both sides of the equation, so we can cancel out this water completely and cancel the coefficient of 2 on this side. So now we're left with magnesium plus 2 hydroxide ions reacts to form magnesium oxide plus 1 molecule of water plus 2 electrons, and then we can add states. So the hydroxide ions are in aqueous conditions, the water is liquid, and the electrons don't have states. So that's how we use COEs and CONES to write our half equations. Okay, now we need to look at calculations involving redox titrations. So there's a number of steps that you can follow. First of all, write a balanced redox equation. Second, calculate the number of mole of the standard solution. That's the solution with an accurately known concentration. Use the mole ratio to determine the number of mole of the unknown that you're trying to solve. Apply any dilution factor if a volumetric flask has been used and an aliquot has been taken from that. Determine the concentration of the unknown solution. And if information is given about two reactants, determine if one is limiting and use the limiting reactant to determine the number of mole of the unknown. So the average concordant titer, which means a maximum range of 0.10 mil, that means that if you've overshot the first titration, you record that in your logbook, but you don't use it in your calculation of your average concordant titer. You only average the 3 concordant titers that you achieve. And don't forget to convert millilitres to litres by dividing by 1,000. Okay, let's look at a worked example. A student reacted 20 mil, this is the aliquot that comes from the pipette, of a standardized solution of 0.0500 molar iodine solution with 20 mil exactly, so that comes out of a pipette or it actually could be out of burette of 0.00250 molar sodium thiosulfate solution. Determine which reactant is limiting and the reactant in excess. So the reaction equation was given. So iodine, 1 iodine, 2 Na2S2O3, 2 NaI, and 1 Na2S4O6. So we know two things about the iodine. So the number of mole of the iodine is concentration times volume. So the concentration is our standardized solution. We need to divide our millilitres by 1,000 to get litres. So that's 0.02000, 3 zeros. Keep those 3 zeros at the end because they are significant. So that equals 0.00100 mole. Now we've got 3 sig figs here, we've got 4 sig figs here, so we want to report our answer to 3 sig figs, the least number of sig figs. We do the same thing, we calculate the number of mole of our other reactant, which is Na2S2O3. Again, we've got concentration and volume. So the equation is number of mole is concentration times volume. So the concentration is 0.00250. The volume is 0.02000. That's dividing mils to get litres. And that means that we've got 5.00 by 10 to the minus 5 mole. Then we have to do a test to find out which reactant is limiting. It doesn't matter which you call the unknown or the known as long as you're consistent. So let's call the unknown the Na2S2O3. The coefficient is 2. The coefficient of iodine is 1. So that means the number of mole of iodine is 2 times 5.00 by 10 to the minus 5 mole equals 0.0001 mole, which is less than the actual amount that we have, 0.00100 mole. Therefore, the I2 is in excess. Na2S2O3 is our limiting reactant. And we use the limiting reactant to answer the final question that we've been asked. but we haven't had that yet. Okay, so there's 1 mark for calculating the number of mole of the iodine, 1 mark for calculating the number of mole of Na2S2O3. There's 1 mark for conducting a test to determine the limiting reactant. That was our number of mole of the unknown divided by number of mole of the known. And a final mark for labelling the reactants either as being the reactant in excess or the limiting reactant. So that's where the 4 marks come from. Okay, so let's look at a worked example. A student obtained the following titers of known concentration of iron 2 sulfate solution, 23.95 mil, 22.85 mil, 22.80 mil, and 22.75 mil, when titrated with 20 mil aliquots taken from a 250 mil solution of potassium permanganate. Write the balanced redox equation and determine the number of mole of the potassium permanganate solution in the 250 ml volumetric flask. So the balanced equation we looked at on a previous slide in this lesson. Now we have to work out the average concordant titer. If we look at our 4 titers, 3 of them are within the maximum range of 0.10 mil of each other, but the first titer is overshot. It's beyond that range. So we still report it in our logbook, but we don't use it in our calculation. So the average concordant titer, we take our 3 concordant titers, we add them together, we divide by the number of samples, in this case 3. So our average concordant titer is 22.80 mil, which is 0.02280 litres. So the number of mole of our iron sulfate, N equals CV, we have the concentration of 0.495 mole per litre by our average concordant titer, 0.02280, because we converted millilitres to litres, equals 0.01129 mole. The number of mole of the permanganate ion, though, is 1/5 of the number of mole of the iron 2 ions. So that's a coefficient of 1, and the iron is coefficient of 5, the iron 2 ions. So we divide our number of mole by 5, and that's the number of mole in our 20 ml aliquot. But the question asks us for the number of mole of the permanganate ions in the volumetric flask. So we actually had a 250 ml flask, and from that we took our aliquot, our 20 ml aliquot. So we need to apply a dilution factor. The 250 comes from the volumetric flask, the 20 comes from the aliquot. 250 divided by 20 is our dilution factor. So that ends up being 0.02822 mole in the 250 ml volumetric flask. Okay, now we're going to look at degree of unsaturation. Unsaturation refers to how many carbon-to-carbon double bonds are present in a fat or an oil or biodiesel. Triglycerides contain 3 fatty acid residues. So triglyceride, we need to look at, are there any carbon-to-carbon double bonds in each of the fatty acid residues in the triglyceride? Oils are liquid at room temperature and often contain 1 or more carbon-to-carbon double bonds. Here's some examples. You don't need to remember these. If you need information, it will be in the data book or in the stem of the question. But what it's trying to show is that the lipid or the fat or oil, depending on its source, they vary in their content of saturated fats, which means carbon-to-carbon single bonds only in the fatty acid residues, or unsaturated fats. So canola oil is 94% unsaturated, whereas coconut fat is only 11% unsaturated. Now, the more saturated the fat, the more likely it's going to be solid at room temperature, and that's when we call it a fat. If the lipid is liquid at room temperature, then we call it an oil. Did you know that coconut oil is actually a solid at room temperature, so it's more appropriate to call it coconut fat rather than coconut oil? Okay, measuring the degree of unsaturation. It's a semi-quantitative analysis, and remember that iodine can be added across carbon-to-carbon double bonds. So drops of an iodine solution are mixed with a fat, oil, fatty acid, or biodiesel, and the number of iodine drops is a relative indication of unsaturation. So we prepare an iodine solution in an appropriate solvent, such as potassium iodide. We add equal volumes of melted fat or oil into equal volumes of a fat-soluble solvent, such as cyclohexane. We add the iodine solution drop by drop. A brown-black iodine will decolorize if the analyte is unsaturated, in other words, if it's got carbon-to-carbon double bonds. And we count the number of drops when iodine no longer decolorizes and the sample remains brown-black. So that's our endpoint. So measuring the degree of unsaturation. An example, linoleic acid is a polyunsaturated fatty acid. It contains 2 carbon-to-carbon double bonds. It reacts in an addition reaction with iodine, where iodine is reduced and the carbons in the carbon-to-carbon double bond are oxidized. So if we have a look at the semi-structural formula, we can see that there's a carbon-to-carbon double bond in linoleic acid, and there are 2 of them, which means each of those is going to react with 1 mole of iodine, and the iodine atoms are added across the carbon-to-carbon double bond, and we go from a brown-black colour of the iodine solution to a colourless solution when iodine is added. Okay, so the iodine value or iodine number is a measure of the degree of unsaturation. So let's have a look at an example. A fatty acid has a molecular formula of C20H32O2 and a molar mass of 304.0 grams per mole. Calculate the mass in grams of iodine that would react with 100 grams of this fatty acid. So the formula we're going to use is the mass of iodine in grams reacted divided by 100 grams of a fat or oil or fatty acid or biodiesel that's being tested. So our number of mole of our fatty acid is the mass of the fatty acid divided by the molar mass of the fatty acid. We have 100 grams of the fatty acid. The molar mass is 304.0 grams per mole. So that means the number of mole of the particular fatty acid is 0.3289 mole. Number of mole of the unknown divided by number of mole of the known. The number of mole of iodine is 4 to 1 because we have 1, 2, 3, 4 carbon-to-carbon double bonds. So we need 4 times as many mole of iodine as the number of mole of the fatty acid. So that's 1.316 mole. The mass of iodine that reacts is number of mole times molar mass. So it's 1.316 mole by 2 by 126.9 is 334 grams to 3 significant figures, because we had 3 significant figures in our 100 gram of the fatty acid. We can use iodine value to predict the relative viscosity of an oil. Remember, viscosity is a measure of the intermolecular forces between adjacent molecules, and a higher IV means a less viscous oil. So if the number of carbon atoms in the oil is constant, then the presence of carbon-to-carbon double bonds in unsaturated oils means that you get more and more kinks in the chain, Rather than if it was a saturated fatty acid, the chains can pack neatly on top of each other in the triglyceride or in the triglyceride. So there's more room for dispersion forces between the layers. If you have unsaturated fats, you get kinks in the molecules, so they can't pack as neatly next to each other, so they're less viscous. So they cannot pack as tightly together, which means there's less dispersion forces between the chains and therefore a lower viscosity. Let's summarise what we've looked at. We've looked at the equipment and the process of a redox titration. To write a simplified balanced overall redox reaction, we can use CoEs in acidic conditions or CoNEs in basic conditions, and we can cancel the electrons, the electrolyte and water. And iodine value is the mass of iodine in grams reacted divided by 100 grams of a fat or oil or fatty acid or biodiesel. Okay, next up is the Chapter 9 progress check. See you then. Bye.